Okay, this is the second video segment for the shell elements because of the canceled lecture yesterday. The first one is already posted. I hope you have watched it. This is that was from chapter 10, and I suggest that you look at the book to see something about the nature of shell elements. Shell elements cover two-dimensional topologies such as instrument panels, let's say pressure vessel, thin wall pressure vessel, hood of a car, and things like that. Now, they go on the surface. They don't have literally any thickness as we did in tetrahedral elements, solid elements. What I would like to do is some more problems. So here is the situation. We have a plate 10 inch by 10 inch, which is subjected to a 10 psi of pressure on each side, on the top side or the bottom side, anyways. Now, the thickness of this part is 0.01. So you have to realize that this must be done with shell elements, okay, not with solid elements. The difference between the one on the left and the one on the right is that for the right one, all four edges are fixed for translational displacement, whereas the one on the left, three edges are fixed for translational displacement. But there's a big difference as far as symmetry is concerned. For example, if you look at the one on the right, all you need to do is to model a quarter of this plate, like that, okay? Whereas here, you need to model half of it. So there's a big difference. I'm going to do the one on the left for you, okay? And then maybe if there's time, I'll do the one on the right. Okay. So let us go to CATIA. This is a wireframe and surface design, and I also want to remind you there is several ways of handling problems with shells. One of them is to create a surface based on extracting surfaces from the solid object. Okay, so you can make a box and extract the face of it. Okay, in this case, for example, it's very straightforward. But if you go that route, then when you go to the generative structural analysis, the box is going to get meshed. And since that is not of interest to you, you have to delete the mesh for the box and the 3D property for the box. The other way is to create the surface directly in wireframe and surface design. Then, of course, there is no three-dimensional object that CATIA is going to mesh, and you have to do the meshing yourself. Okay, so on a convenient plane, on this vertical plane, I will sketch a line which is 5 inches long, because it was half of the geometry that we're going to model. So let's dimension this thing to be 5 inches. Okay, exit and extrude it by let me see, by 5 inches in each direction. 5 inches, mirror extend, and say OK. There we are. This is what we need. Now let's say that this is made out of steel. So why don't we create a property, material property, metal, let's say steel on the part, and we say OK. And we're done here. This line we can just hide it. All right. So we now go to generative structure analysis. Okay, we are doing a static analysis. Let me change the rendering here. The color ivory means that we are dealing with the surface, by the way. Now notice that there was no 3D object involved. This is why CATIA did not mesh anything for you. So now you have to go and create your own shell mesh, which is right here. And this is not a fancy mesh. If you go to advanced meshing tool, there are fancy meshes that you can make. Maybe I'll take you later there, but right now I'll just use the octave triangle mesher. So you click on it, you select that. It will create a mesh of this size for you. Let me make this thing a little bit smaller. So how about maybe, I don't know, 10 inches, 10 millimeters. You can see that it's a lot smaller, and you can actually see the mesh if you want, in the same ways that you did before. Right there, there's your mesh, and then to do the rest of the problem, you deactivate it. Okay, then it's the 2D property. This is the 1D property for beam. This is 3D property for shells, for solids, which you don't have any, and there's 2D property. You click on it, you click the surface that you want, and material is going to be picked, steel, and then you put appropriate thickness. I said 0.01 inch, so 0.01 IN, and you say OK. That's pretty much it. So now it comes the rest of the problem. So user-defined restraint. This edge and that edge are fixed from moving in the X, Y, Z direction. 3 translational rotations, 3 translational displacement are fixed. Now this edge is a plane of symmetry. So you click on that edge and uncheck these to start from fresh. Notice that the edge here, the red one that I picked, lies in XZ plane, or a plane that is parallel to the XZ plane. So the rule is that if it's in the XZ plane, it does not move in the direction Y. Just like beams, rotations are going to be exactly opposite. So it's going to be check this and check that, and OK. And then again, click on this edge. This is also a symmetry plane. Oh no, sorry, this is not a symmetry plane. This is the case that we're looking at where there was only one plane of symmetry. So cancel that. There's only one plane of symmetry, and we did it. Okay, so it's right here. All right, good. This is a free edge. Okay, let me bring that here. We are doing this problem, and the one that I just pointed to is the free edge. It's right there. Okay. Now let's apply a pressure on this. Pressure on that face, and I did say 10 psi. 10 psi. Okay, good. Let's run it. It's done. So let's look at the deflections. Change the rendering. That doesn't surprise you. This edge, this point is going to deflect the most. You can look at the stresses, one meter stress. Because this point deflects the most, the bending stress is the biggest here, and it has the biggest stress. It's very similar to a simply supported beam that the biggest stress is right in the middle. All right, so now of course in real life you have to look at the numbers as far as the value of the stress is concerned. And this right now, since I've not changed my units to PSI, let me actually leave it like this. So let's see now. It says 46 times 10 to the 9 Pascal. That's what it is. Okay. Now, if you that means 46 gigapascal, correct? Okay. Now, the rule of thumb for yield stress value, this is a rule of thumb only, is take the Young's modulus of the material, which is still 200 gigapascal, and divide it by 1,000, and that will give you the yield stress. So 200 gigapascal divided by 1,000, it's going to be giving you 0. Divided by 1,000. Let's see now. It's going to give you 0.0. Actually 0.2 gigapascal. What we've got is 46 gigapascal. That means the load is too much for that thickness. So as far as far as getting colors and doing the problem is concerned, we're done. But in real life, this is too thin. So for example, if I go here and increase the thickness, notice that it's 0.25 millimeters, similar to aluminum foil. So let me make it 0.1 inch instead of 0.01 inch. This is now 2.5 millimeter. We run it. And look at the 1 meter stress. Now it is, let's see now, 4.46 10 to the 9, okay? So this is 0.46 gigapascal. And it's still double the yield value for steel if we go with the rule of thumb. Okay, so obviously it has to be either you have to reduce the load, you have to increase the thickness, or you change the dimension of the problem. Now I'm going to stop here. We'll redo this problem if I actually went and created the box, and which means I have to delete the 3D mesh, etc. So I'm going to stop there. That's going to be video segment 3.